Hey everyone, Mr. Shatter here to continue learning about functions from derivatives, this time looking at the second derivative. Objectives of this video to examine the concept of concavity and to use the second derivative test to find extreme values of f of x. Let's jump in. So, first up, definition of concavity. A graph is said to be concave up if its first derivative increases, and concave down if its first derivative decreases. So look at the relationships of the tangent. So the positive one, for example, if you keep drawing tangents as x grows, notice that the slope of your tangents is increasing. They're getting steeper and steeper and steeper. And the same in the negative region. And so that's what concavity actually is. So things that are concave up tend to have a U shape or part of a U. So it could be like the left branch of the U or the right branch of the U. That shape is said to be concave up, where a figure that's concave down typically takes an upside down U shape, or part of it. You know, it doesn't have to be the whole U. It could be a segment of the U. Like for example, look right here in the concave down region. It's like the left half of a U. So whenever you have that upside down U shape, that's a sign of something being concave down, and the right side up being concave up. But we typically use, increasing and decreasing. We use the derivative, right? And the derivative of the derivative is known as the second derivative. So the more formal definition of concavity is something's concave up when y double prime is positive, which is the second derivative, and concave down when y double prime is negative, okay? The stipulation this time is that f is twice differentiable, meaning that its derivative is continuous and the second derivative is continuous. That's an original function being twice differentiable, means you can go two derivatives down without running into any discontinuities. All right, so that's concavity. A point of inflection is known as a change in concavity, okay? So a point of inflection is basically when something changes from concave up to concave down, or concave down to concave up. So it's kind of like, when we had a sign chart of the derivative when you look for extrema. It's a very similar thing here, is you're making sign charts for the second derivative and you're looking for a change in concavity. Here's a little summary of everything that we've done in the past two videos. This will help you kind of summarize the first and second derivative tests and what you're looking for. Okay, so here's the second derivative test in words. This is a little bit different than the first derivative test. It says if f prime of c is 0, whoops, literally crossed it out there. If f prime of c is equal to 0, okay, and f double prime of c is less than 0, so that's concave down, first derivative is 0, not undefined. We're only talking about 0 here. Then f has a local maximum at x equals c, okay? Reverse situation. F prime of c is equal to 0, and f double prime of c is greater than 0, and f has a local minimum at x equals c. So in the situation where we are concave down, we are negative, you're going to have a maximum. Think about concave down, meaning like the upside down u, maximum. And think about concave up being an right side up u, and therefore you have a minimum. Here are a couple of examples of graphs basically pertaining to the definitions of the first and second derivative test. Okay, let's try an example using the second derivative test. In this problem, it says use the second derivative test to find extrema of f and find any points of inflection of f of x. So the second derivative test, first of all, you have to find the first derivative. And the first derivative is 3x squared minus 12, okay? Actually, I think this example is the same one we did in the previous video. And then you have to find the critical points, or the values that it's going to be 0, okay? We're not going to look at undefined values in the second derivative test, just zeros of the derivative. So we know if we set this equal to this, we can factor this, and we know that we could factor it into the difference of two squares. And so then we get positive 2 and negative 2. And these are the instances when f prime of x is equal to 0. We need those. We need these in order to do the second derivative test. But unlike the first derivative test, in order to do the second derivative test, you need the second derivative. Oh, I'm not sure what I was going for there, but it didn't work for me. So we'll put the x back in there. The second derivative, I'm just going to differentiate this. There's no need to differentiate the factored form. 3 times 2 is 6x, and the derivative of negative 12 is, of course, 0. So this is the second derivative. And what I'm going to do is I'm going to find out where you have concavity, concave up, concave down, and that's just basically where it's positive and negative. So in order to do that, I need to first figure out where it's 0, and I know that that's equal to 0 at 0. So I'm going to do a sign chart, this time of the second derivative. I'm going to put 0 here. And I know if I test negative values, I get a negative second derivative. And if I test positive values, I get a positive second derivative. So this right here, from negative infinity all the way to 0, is where the original function, the original, is concave down. And from 0 all the way to positive infinity, this region right here, I know the original function is concave up. Okay? So if I use the second derivative test, it tells me this. Let's first consider x equals positive 2. X equals positive 2 is right here, right? Positive 2 is like right here. So at x equals positive 2, f prime of x equals 0, and f double prime of x is greater than 0. It's positive, right? Which means I have that concave up shape. So f of x has a local minimum of negative 21 at x equals 2. And that's by the second derivative test. So the second derivative test uses the zeros of the first derivative, and then of course you have your concavity. That tells you if it's a max or a min. And let's do another one. So at x equals negative 2, f prime of x equals 0, and f double prime of x is less than 0. Here's negative 2 right here, right? So f of x has a local maximum. Remember, if it's concave down, it looks like an upside down U. So it's a max. So local maximum of, and this one came out to 11 at x equals negative 2. At x equals negative 2. That's a terrible x. And we'll fix that. There you go. And by the same argument we made in the problem when we did it last time, these are locals. They're not absolutes because the end behavior goes to negative infinity and infinity. We do have a point of inflection. F of x has a point of inflection, POI, I usually abbreviate it, at x equals 0, since f double prime x changes from negative to positive. Just barely fit it right there, negative to positive. And that's verification of a point of inflection. Okay, so let's look at this example right here. Now this example is basically telling us what information can you pull from the graph of a derivative about the original f of x. And the first thing you could do is you could look right up here and you could say, okay, let's talk about positive values of this derivative, okay? Positive values of this derivative. So we'll write positive first derivative leads to increasing function. Okay? So positive values of the first derivative leads to an increasing function. And then we know if I change the color here, which I'm not quite sure is going to show up, I'm going to look, it looks yellow. But it's orange. It's supposed to be orange. Negative first derivative yields a decreasing original function. Okay? So that's kind of a review from the previous unit, the first derivative test. Well, let's do some more interesting changes. We know that that this right here is I'm going to switch back to yellow, is a decreasing first derivative, right? A decreasing first derivative. And I know that a decreasing first derivative is going to yield a negative second derivative. So I know that f double prime x is less than 0 right from here to here. And then I know I'm going to swap right here. I'm going to swap in this little interval. When f prime of x is increasing, I know that f double prime of x is positive from there to there, right? And then I could continue, and I could move down here, and I know that it's negative from here to here, and it's positive from here to here. And that gives me concavity directly. A negative second derivative yields concave down intervals, and a positive second derivative yields concave up. Remember that this is the graph of the derivative, so don't try to look for the u in the upside down u shapes. We're looking at the derivative here. That only works when looking at the original. Also, I know right here at -2, right here at 0, and right here at 3, I have points of inflection. The definition of a point of inflection is a change in concavity, so positive to negative or negative to positive. And that's how using the graph of a derivative can help us figure out what the original function is doing. Let's take a look at an example. This is example 3 now, and this particular problem is actually an AP question, an old AP question, FRQ, and it gives you the graph of this right here is the derivative of f, not the graph of f, and it also tells you again right here that y equals f prime of x. And then it tells you again right here, the figure above shows the graph f prime, the derivative of f. So make sure you understand that the graph you're looking at is the derivative, not the original function. The function, or the words go on to say, the domain of f is the set of all real numbers between -3 and 5, not inclusive. Okay. A, for what values of x does f have a relative maximum and y? So I know that I have a relative maximum when looking at the derivative, and the derivative changes from positive to negative. Excuse me. So I need to cross the x-axis, right? Changing from positive to negative occurs right here at -2. So x equals -2 since f prime changes from negative to, positive to negative doing max, thinking ahead to the next question, positive to negative. Okay, so that is, and I'm going to scooch up so I can fit the next one, that is an appropriate response for letter A. Letter B, for what values of x does f have a relative minimum? Well, relative minimum is going to occur when I change between negative and positive, right? And that's going to occur right here at x equals 4. X equals 4 since f prime changes from negative, this time negative to positive. Negative to positive. So that is where you have a relative minimum. C, on what intervals is the graph of f concave upwards? Use f prime to justify your answer. Well, remember, concave up is basically positive second derivative. And I have the first derivative in front of me. So positive second derivative will be where the first derivative increases. So I'm not increasing at -3. I'm not increasing until I get here, -1. And I will increase all the way to 1. So -1 to 1, I'll start there. So -1 to 1, union, and I'm also going to increase again beginning at 3 and working my way to 5. So 3 to 5. Since f prime of x increases. So the first derivative increasing shows me where the second derivative would be positive, aka concave up. D, suppose f of 1 is 0. Graph the function f from 0 to 2. I'm just going to do it right on top of the function here. Okay, so I'm going to go ahead and graph this. Now here's what I know. F of 1 is 0. So f of 1 is 0. I'm going to put that, actually I'm going to use a red or something. I'll use a blue, nice blue. Here we go. F of 1 is 0. And in order to understand the general shape, I'm going to use the concavity. I just said that the graph is concave up from -1 to 1. Okay, so that means that from 0 to 1, which is included in my interval, I am concave up. And I also know that from 0 to 1, so from 1 to 2, I am concave down, because I know that I'm decreasing from 1 to 2. My first derivative decreases. So if I want to be concave up from 0 to 1, I make that U shape. I make that little U shape, just like this. And then from 1 to 2, I make the upside down U shape, right? And in order to change from concave up to concave down, I know I have to have a point of inflection, which is basically a change in concavity. So what I'm going to do in order to do this is half of the graph from 0 to 1 is going to be a concave up graph. Oops, don't make a straight line. It's going to be a concave up graph. It's going to look like this. And then I know that from 1 to 2, I'm going to start to be concave down. I'm going to get that upside down U shape going, upside down U shape. So this is one example of what f of x could look like. This is f of x, the original, from over the interval 0 to 2 open interval.